So now that you've had a chance to take a look at all the different ways of programming the Java fork join framework by using the iterative approach and a couple of recursive decomposition approaches, let's actually go ahead and compare and contrast the performance of all these different models and see which one actually does the best. And the results are a little bit surprising here. So each of the Java fork join programming models we've looked at has various pros and cons. So the iterative approach, the apply all iter model that we looked at first, its main virtue is it's relatively simple to program and relatively simple to understand. As you can see here, all it's doing is it's just going through the list of elements that are in the list, and then it's going ahead and creating a new recursive task to process that element. It forks that task to arrange it to run in parallel in the fork join pool, and then it adds it to the forks list. And when we're done doing all the forking, then we just go through the forks list and we basically join on every task or subtask and then add the results to the results list, or the results list that we are going to return as the return value from the apply all iter method. The downside with this approach, as you can see by the stats that we're showing here, which we got just by calling some helper methods that are defined in the fork join pool interface, we're actually incurring a fair amount of work stealing. And that's because all those subtasks, all the ones that go here, are originally put into the calling thread, and then they have to be stolen by all the other threads in the pool. And so there's a lot more stealing taking place. And as you can see here, if you take a look at the results, we print the results out from fastest to slowest, and perhaps not surprisingly, the apply all iter test executes slowest because it's got more stealing going on. These tests were run on an earlier implementation of my laptop, which has 6 cores. I now have an 8-core laptop, so I should probably rerun the test to see if it runs any faster. So as a consequence, you can basically see the correlation between the amount of work stealing and performance. So all things being equal, you'd prefer to come up with a solution that doesn't require as much work stealing, because that will incur lower overhead and therefore perform better, as we'll see as we look at some of the other examples. In contrast to the apply all iter implementation, the recursive decomposition versions incur fewer steals. So you can see that we have apply all split index and apply all split and apply all split index EX, which is the one that gets rid of some of the copying overhead as well. And those incur less stealing because they do a better job of recursively decomposing the work into this kind of balanced tree of cores and threads. And therefore, as a consequence of this, the performance is better. So you can see that, for example, the test apply all split index EX, which is the version that uses the recursive action and the array is passed in as a parameter, so we don't have to do any funky reflection or any extra conversions or copying, that performs the best of the different models. And there are other factors here that are making a difference, such as less data copying for the apply all split index EX implementation. So you can see that there are various factors that are being traded off here, and being more clever can give you a better boost in overall performance. However, I think you'd also agree that the implementation that uses the splitting, either the one that does the splitting with the list or the one that does the splitting with the indices, irrespective of what you're splitting, the recursive implementation is more complicated to program. Now, once you understand the basic model of this fork join pool framework, then it's really not that complicated because it's kind of paint by numbers. It always looks more or less the same. But at first glance, it can feel a little bit daunting. And it also has this extra work in terms of method calls because it has to do these things recursive. Another thing to note here is that the recursive actions overhead is lower than the recursive tasks overhead. And that's because the recursive action is just storing the results into this array rather than doing sublists. So obviously sublists have some additional overhead that just storing things directly into an array do not. But it's also fair to say that the recursive action implementation is a bit more idiosyncratic, at least the one where you have to use the reflection capabilities of Java to make a generic array. Although I have to say, this is a very useful idiom to understand if you're stuck in a situation where you need to make a generic array in order for your program to work properly. Now, the way to fix this problem, as we saw, was just to change the API ever so much so that we're getting the results back as an array as opposed to having to convert it back to a list. So here's the really interesting part. Ironically, the most concise solution doesn't actually use the Java fork join pool directly, but instead uses a Java parallel stream. Now, again, this is a bit outside the scope of this particular class, but I think it's worth being aware of. So if you take a look at my program, the test program, there's yet another implementation called apply parallel stream. And this is super, super simple. And as we'll see in a moment, also very efficient. So as you can see, the parameters and the return value are similar. They're basically what we had before. And under the hood, the parallel streams framework uses the common fork join pool. So we don't have to pass in a fork join pool parameter because we're going to just use the common fork join pool. So the first thing we do is we take the list parameter and we convert the list into a parallel stream by using the parallel stream factory method. We then call the map intermediate operation, which will apply the op function to each element of the stream in parallel. And then we take all those elements and we collect them together using the Java toList collector, which comes out of the box with the collectors utility class. And what that does is it takes the stream of transformed operations and then it collects them back into a list, which is then returned as the return value from apply parallel stream. So here's the really fun part. If you take a look at this, then you can see that the parallel stream version actually runs very well. It runs pretty efficiently. And it's also much easier to program than all the implementations that use the fork join pool directly. So, and of course, your mileage may vary. So on other platforms you may find, or other hardware, or other times when you run the program, depending on the phase of the moon, or whether you throw salt over your shoulder or whatnot, you may actually find that sometimes the parallel stream implementation actually performs the best. So that's a great example of the power of abstraction, where you can use these higher level parallel programming frameworks like parallel streams, and your code becomes very, very simple. You get all the benefits of the fork join pool processing model without having to wrestle with any of the complexities of programming fork join pool directly. So that's pretty cool. So that's the end of our discussion, where we compare and contrast all these different programming models that use the Java fork join framework, either directly or indirectly. And so at this point, you should have a much better understanding of how things are working under the hood. One thing I will point out, by the way, just to give you a little context, the parallel stream model actually does a recursive decomposition-like approach, and it's very cleverly implemented. And if you take my other course that'll be coming up next fall, I'll actually walk through the implementation of parallel streams in some detail. You can always go back and watch those videos from other playlists on YouTube. So bottom line is, parallel streams are very carefully optimized under the hood to perform extremely well, as you can see with these results in this particular experiment.